All right, welcome back to the Kitchen Research Group. It's been a while and we've had a few papers come out since the last video. So today I'm going to tell you about investigating the error imbalance of large-scale machine learning potentials in catalysis. This was published recently in Catalysis Science and Technology in a special issue on data science in catalysis. So the main thing that we tried to do in this paper, in a nutshell, is try to figure out why we've seen this plateau in the accuracy over the last few years in accuracy of machine learned potentials. So these are machine learning models trained on very large, millions of data points, data sets, and you can see back in 2021 the errors were modestly high, and they've come down as the models have gotten larger and more sophisticated with different features like equivariance and different angles and bond lengths and dihedral angles, etc. But what we noticed is over the past 2 years, it's really plateaued around 0.2 EV for the MAE, and we thought maybe this means that the models are no longer able to improve because there might be some underlying error distribution we weren't aware of. So even though the models get better and larger, we see this kind of plateau, and so we wanted to look at what was happening. So we had two hypotheses. The first one was maybe this is convergence errors. In DFT, you have to choose plane wave cutoffs and K-points and other things, and you always make a compromise on accuracy and speed. And we thought maybe there was a convergence error that we would be able to find. And the second is we looked at inconsistently labeled data. I'll talk about what I mean by that. And in a nutshell, we've mostly found this inconsistent data is largely responsible for this energy plateau. And I should note the forces don't show this. The forces have been getting consistently better all along. And the forces are the derivative of this energy. And so any of these kinds of inconsistencies kind of get removed in the derivative. But the trouble is we want the energy for lots of thermodynamic properties, and we basically don't want to have to integrate forces to get to that. Okay, so let's talk about convergence errors. Again, in DFT, we make a unit cell with the atoms. We already make some approximation that the unit cell describes the material, and there aren't longer range things like defects, etc. That's not really the issue at hand here. What is true is that you have to choose a plane wave cutoff to expand the density in. You have to choose a K-point density, and the higher these are, the more accurate your calculations usually are, or at least they're more converged and not dependent on them. But that also increases the cost. So if we look across here, we're going to just look at two of the parameters, the plane wave cutoff and sigma. This is a smearing factor. We found K-points were so well converged it's not even worth talking about. What you can see in the original OC20 settings, we chose 350 EV cutoff, and you see a quite high range of variations if we compare from 350 to 500. So if we look at the change in energy from NCUT 350 to 550, you see there's several EV range. That implies 350 is not a particularly well converged NCUT. Now that's a little bit misleading because we don't actually care about the total energies. We always subtract energies in calculating an adsorption energy, and if the error is the same in both of them, that effect largely cancels, and that's shown over here on the right, that for different classes of materials, the adsorption energy is in fact quite well converged at this setting of 350 and at this setting of sigma. So even though we do see quite big changes in energy as we change the NCUT and as we change sigma, it is not likely to be the result in the large MAEs we see because of cancellation of errors. Now that's specific to this example. We are subtracting similar systems. The slab and the slab adsorbate are quite similar, so we expect for the most part the errors to largely cancel, and that's what you see over here. The errors are really quite small across all the classes. All right, so we don't think that this is the reason why we see the plateau. What does turn out to be the reason is what I'm going to call inconsistently labeled data. And what I mean by inconsistent is we usually calculate an adsorption energy, and that adsorption energy would be like up here at the top, this slab plus adsorbate minus a similar slab minus the adsorbate energy. We call that the adsorbate energy. But it turns out that a lot of the materials reconstruct. And so instead of getting two slabs that are similar on each side, we get a reconstructed slab with the adsorbate, and then we subtract off the unreconstructed slab. And what that means is we don't have an adsorption energy, we have an adsorption plus a reconstruction. That's what I mean by inconsistent. The model is trying to learn what we call the adsorption energy, but sometimes we're getting this extra contribution. And that inconsistency leads to big errors. And what we found is that the inconsistency, this reconstruction fraction, it could be as high as 50% for, say, the halides, and notable for metalloids and nonmetals. And so this is what causes a lot of the errors. When we look at the big errors, they're almost all reconstructed surfaces, and that's because the label isn't consistent across the data set when we define it like this. And if we take these out, you can see here we reduce the errors quite substantially. We still have the largest errors in nonmetals and halides. Those are not well balanced in the data set. There's not as many examples of these, and so the model also just can't fit those particular classes as well. Now, a solution to this is to not fit adsorption energies. We like adsorption energies because the error cancellation for the most part is already built in, except when it reconstructs, and we don't have a good solution for that. And a potential solution is to fit total energies. So if we fit the total energies, then we don't have this reference problem. We don't have any inconsistent data. And what we found by fitting the total energies is that we do end up getting some higher MAEs in the individual components. Out of domain in particular is always a challenge. And but when we take the difference, we see the same kind of cancellation of errors. And so we can use all the data for the total energy models and get comparable MAEs in this case to the adsorption energy model. And then we don't have to worry about this inconsistent label. All right, so in conclusion, in this data set for adsorption energies, there are convergence errors in the individual components, but in the end, cancellation of errors don't affect the MAE that significantly. Now, that might not be the case if you were trying to look at other systems. Every system has its own cancellation of errors that you have to address. But in this case, we don't think that convergence errors were critical. Not the most critical. We did find that inconsistently labeled data using adsorption energy is mostly the main cause of the errors in the previous models. If you take them out, the MAEs get better because you have more consistent labels, and the inconsistency comes about from the contributions of reconstruction. These are much more frequent in nonmetals and halides. Maybe that's because of the high throughput system made initial guesses that promoted the reconstructions or something like that. But again, if we take those out, we get better models. And if we use total energy models, then we can use all the data and end up with similar accuracy for the OC20 data. I think similar things are probably true in the OC22 data. Things get a little bit more complicated with the oxides. In addition to all of the things I talked about here, we have different spin states and the potential contributions of DFT plus U, but we didn't get to look at that in this work. So I hope you learned something in this, and certainly this will change the way we approach building these large data sets to do hopefully a better job in the future of ensuring consistency and using the large errors to inspect those systems and look for reasons why they're not consistent or look for errors that are present in them. So that's it for this video, and we'll see you next time.